Team, we're looking at the periodic table today, so let's start off with some basics before we get into the nitty and gritty information. 3 terms for you: elements, compounds, molecules. Let's first look at elements and compounds. Now look to the right here, you will notice that these elements here are made up of just one atom. Take your ozone for example, only oxygen. Take your chlorine gas, only chlorine. That is what you call an element. But as soon as we add another atom into the picture, you've got what you call a compound. Take your water for example, you've not only got just oxygen on its own like the ozone, but you've actually got hydrogen as well. Your molecule is the smallest particle that can exist independently. So let's take your glass of water that you may have drunk from this morning. You don't just say it's a molecule of water for the whole glass, you've got to look at the smallest subunit, and that is your H2O, that is the molecule. So it's like an umbrella term for describing the smallest particle that can exist on its own. Let's go down even more basic and smaller into the atom. 3 subatomic particles: your electrons, protons, neutrons. Let's look at the charges first. Your electrons are negatively charged and they orbit the nucleus. In the nucleus we've got your protons and your neutrons, and like the P in front of protons, the protons are positive, and like the sound or what neutrons sound like, they are neutral. In terms of mass, protons and neutrons are relatively the same, so we give them a number of 1, and electrons are a lot smaller, so they are not involved in the mass of the atom because they're quite insignificant. Interestingly enough, most of the atom is actually empty space, but these are the main subatomic particles that have been found at this stage. Let's finally jump into the periodic table. Now we've got our fella over here, this is Paul the proton. Basically, our protons are what give us the atomic numbers, and it's actually how the elements are arranged on the periodic table. So 1 proton for hydrogen, let's put you in first with a atomic number of 1. As soon as we have 2 protons, we have helium, 3 protons, lithium, beryllium, etc. So that is how they've been arranged in the end. If you want to look into the history of the periodic table, it has gone through a fair few changes, and this is what we've stuck to at this stage. Furthermore, with the atomic number, let's look at some examples. If I asked you for the atomic number of helium, you just have to look at the smaller number generally. Remember, they can be shown differently when you get questions based on this, but the smaller number is the atomic number and the number of protons. If I ask you the same for carbon, again, the smaller number is the atomic number and the protons. Lithium, same deal. Please note that the mass number here is very different to what we have on the periodic table, and that is something you'll learn about later. The mass number shown here is just really the number of neutrons and protons combined. Let's look into that new member. We mentioned neutrons. This is Neil the Neutrons. Please don't judge me for the weird names, I'm trying to make it interesting. And basically, when the number of neutrons change, you actually have something called isotopes. So really, what I like to think of is Paul, the proton, actually gives the element or the atom its identity. It says this is a helium, this is a carbon, but Neil doesn't impact the identity as much. All it does is it forms different isotopes of that atom. So for example, we've got our hydrogens over here. Notice they all have 1 proton, which is what gives them the identity of the hydrogen, but they have different numbers of neutrons. And all that basically changes is the mass number, but they still remain a hydrogen, but they are different isotopes. This is also something interesting to look into, how stable and unstable your atom gets as you add more and more neutrons into the picture. Now, what kind of questions could you get? Let's look at the atomic mass that I mentioned before. We talked about the atomic number, which is the protons, and the atomic mass, which is the protons plus the neutrons. So these are the 2 numbers represented over here. If I asked you, hey, atomic number of chlorine is 17, how many protons does it have? We already know it's 17. But if I give you the mass number of 37 and I ask you, hey, how do you work out the number of protons and neutrons in its nucleus? What would you do? I want you to pause the video and have a go before we start discussing this. How'd you go? Let's take a look at the answers now. So as we discussed, it has 17 protons. We now have figured out that it's got 20 neutrons. How on earth did we work it out? All you have to do is take the mass number away from the atomic number. Why? The mass number is the neutrons plus the protons, and the atomic number is just the protons. So as soon as you take that away, you are left with the number of neutrons. And make sure to explain this completely if the question asked you to explain how you work this out. Let's try some more questions. Have a go. Which of the following are isotopes? I've given them fake elemental names over here, W, Y, etc. Have a go. How do you identify which are the same isotopes? Have a go. Right, how'd you go? Let's take a look at the answers. Again, this is kind of looking at the identity. And remember, the identity is represented by the smaller number, which is the atomic number or the number of protons. And you will notice that W and Y have the same number of protons. Hence, they are the same isotope. Sorry, they are the same element, but different isotopes. So we both know that Y and W are different isotopes of each other. Okay. Now, we looked at the impact of the number of protons, we looked at the impact of the number of neutrons changing. Let's take a look at what impact electrons have on your atom. We basically organise these into specific shells. Down the track you'll learn about clouds, but for now we keep it simple with shells. We actually use a formula for these shells as well. This is a formula of 2n squared. What on earth does n stand for, right? That stands for the shell that you're looking at. So in this example here, we've got 3 shells, and if we want to pick one shell and figure out the maximum number of electrons in the shell, all we do is pick the number. Let's say I want to figure out how many electrons can I fit in a maximum of this shell. I pick 2, so I go 2, n squared. N squared is 2 times 2 to the power of 2 is 4, times by 2 is 8, so that means a maximum of 8 electrons can be on this second shell. If I do the same for the fourth shell, I get 32 electrons on that shell. Please note though that you will notice that it usually goes 2, 8, 8, because the 18 just represents how much can fit if it's a maximum number of electrons, but generally we usually go 2, 8, and it just fills to 8 electrons in the third as well. Also, another really good term is your valence shell. That represents the outermost shell of your specific atom. So for example, in this atom over here, your valence shell is the third shell. This one has an important role in how your atom behaves, and we'll talk about that a little bit later too. Let's take a look at some questions if I ask you for the electron configuration. So if I said, hey, for lithium down here, could you give me the configuration of it, please? All you have to do is in the first one you mention how many electrons in the first shell, which you know is 2, how many electrons in the second shell, which is 1, etc, etc. Now, I'm going to put a question to you. If I wanted aluminium, how would I go about the electron configuration? Have a go in your head before looking at the screen. If you got 2, 8, and you jumped onto the next shell for your 3 remaining electrons, you would be spot on. Now, question is, where on earth do you find out how many electrons this actual atom involves, right? That, luckily, is the same as the number of protons for the actual atom. This is in the example of the atom being neutral, which means you've got the same number of protons and electrons in the situation. Now, another question. You have sodium, and I've given you up here the atomic number or the number of electrons because it's neutral, and I've also given you the electron configuration. Can you please have a go at these questions? Pause the video. How was that? Let's have a look at the answers. So we figured out the atomic number is 11. How many valence electrons are there? Remember, valence shell is the outermost shells. So the valence electron is how many electrons are on this outermost shell, which is 1. What group is it in? We'll figure this out later on. The actual number of electrons represent the group it is, the number of electrons in the valence shell. How many electron shells does sodium have? You just have to find out the electron configuration if you don't have it already. And what period is it in? You actually count how many shells it has, and that tells you the period. Try a few more for me. Draw the electron configuration for the first 18 elements. You may want to just do a few, but if you're really feeling up for a challenge, go for it. Pause the video. Why on earth would I get you to write them all out? It's because I'm just a pain and I'm evil? No, it's because there's actually a little trend that I just mentioned before. What do you notice in your first period? There's only 1 shell involved. Second period, 2 shells are filled. Third period, 3 shells, etc. Groups. How many electrons on the outermost shell for the first group? 1 electron. Second group, 2, etc, etc. So that is just another way of how the periodic table can be used as a cheat sheet for identifying the subatomic particles involved, and later on you'll learn that impacts how it interacts in reactions as well. I didn't really give Eric the electron the honourable mention that I should have last time, so let's focus a little bit about electrons now. Basically, I mentioned before that if your atom is neutral, you've got the same number of electrons and protons. However, this can actually change, and this is where we look at ions. We've got 2 types of ions generally, the cations and the anions, and I use a very silly example. Your cations are the positive ions, and your anions, which is actually not spelled with an O, but an AN, is where you've got a negative atom. Basically, you just have examples where your atom has either lost an electron and becomes a cation, because now you have more protons than electrons overall. And if it actually gains an electron, which can actually happen, you actually have a situation where your overall atom is now negative and it has more electrons than protons. And we indicate this with charges, and you'll learn more about this later. Thanks for listening, everyone.